The next trend in the periodic table that we are going to take a look at is the ionization energy, which is the energy that required to remove an electron from the gaseous state of either neutral atom or ions. Because an atom contains several electrons, therefore each electron will require a certain amount of energy to be removed. The first electron that is removed from the neutral atoms, the energy that required for that is called the first ionization energy. So if you want to represent this as a chemical equation, X would be the chemical symbol for a certain element that is going to present in the gaseous state. Okay, so if the element is present in the solid or liquid state, those elements will need to vaporize into gaseous state first before the electron can be removed. And once the electron is removed, then the product of this would become cation, right? Notice that this is neutral, and once electron is removed, it's going to become cation, and the product of this process also going to include electron as well, because you are removing electron out of the neutral atom. Therefore, the neutral atom now become cation, and you are going to get the byproduct of electron as well. The energy that associated with this is the first ionization energy. So subscript 1 refer to the first electron that is removed, and this is the amount of energy that is causing the neutral atom is become ion, right, or what we call ionization. Okay, this process is considered to be the process that require energy. So the amount of energy or the amount of the first ionization energy will come out to be a positive. Okay, so indicate that the system requires energy. This process is called endothermic process. The trend of the value of the ionization energy is determined by the size of an atom. So let's take a look at when we go down the column first. If we are looking at the periodic table and we are going down the group, right, from top to bottom, you will see that the atomic radii will increase because the energy shell increase. The atomic size will get bigger as you go from top to bottom. And as the size is getting bigger, if you compare between the two, right, so if you have a bigger size versus the smaller size, and this one right here would refer to the nucleus, right? And the outer shell would be the location of where the electron is located. You will see that the bigger size, right? The electron of the outer shell is further away from the nucleus, therefore it's going to have a weak interaction with the nucleus. However, the smaller size the electron would the electron is closer to the nucleus, therefore it's going to have a stronger interaction with the nucleus. Therefore, in this case, the nucleus would hold electron more strongly, right? So this is going to be a strong attractive force, right, between the electron and the nucleus. But the bigger size, you are going to end up with a weaker attraction between the nucleus and the electron. Therefore, in this case, the bigger atomic size would be easier to remove electrons. So this is going to result in easier to remove electron. Okay, and the one that the electron that experiences a stronger attraction force would going to be harder to remove, right? So this would be hard. Oops, sorry. Okay, let me rewrite that again. That would be harder to remove electron. When it's easy to remove electron, it doesn't require a lot of energy at all. That means this electron right here can just be removed easily. Therefore, it's going to require less energy, right, to remove this electron. However, the one that is going to require is harder to remove electron is going to require more energy to remove electron. Therefore, in this case, if you're looking at the two different sizes of an atom, the smaller size would have higher first ionization energy than the bigger size, because the smaller size, the electron experience a stronger attraction between nucleus and electron. Therefore, it's going to require more energy to pull out this electron. Okay, so that means as I explained earlier, so you can write as the atomic radii increase, it's easier to remove electron from the outer electron, right? And then you are going to observe that the trend of the first ionization as it's going to decrease as the atomic size getting bigger. Okay. Now, if you go from left to right across the periodic table, right, from left to right, if you are talking about the same number of energy shells, you will see that going from left to right, you are increasing the effective nuclear charge. Okay, so effective nuclear charge going from left to right will increase if you are looking at the same number of energy shells. Okay, so as the effective nuclear charge increase, that is going to imply that the electron, the outer electron, is going to experience a stronger attractive force between nucleus and electron. Therefore, in this case, the higher effective nuclear charge, the atom going to experience a stronger attraction force, so therefore it's going to be harder to remove electron. So this also affect the size of an atom as well, right? Because as we know that effective nuclear charge increase, the nucleus will be able to pull electron closer to itself. Therefore, going from left to right, you are going to observe that the size of atom would also decrease as well, right? So it's going to decrease from a bigger size to a smaller size. Even though they have the same number of shells, they are going to still having a different size because of they having the different effective nuclear charge. Okay, so that means in summary of this is that as we go from left to right across the periodic table, the atomic radii will decrease because the effective nuclear charge increased, right? Therefore, it's going to be harder to remove an outer electron. Therefore, in this case, you are going to observe the ionization energy going to increases. Okay, so with that being said, if you are looking at an example here, if you're looking at the in comparison between phosphorus and arsenic, right? So we are going to look at the highest first ionization energy. Therefore, you will need to know first that the highest ionization energy would associate with hardest to remove electron. Remember from the previous slide, we talked about this before, that if it's easy to remove electron, the ionization or the amount of ionization energy would be low, right? Because it doesn't require much of energy. Whereas if it's hard to remove electron, the system going to require more energy. Therefore, the first ionization energy would be high, right? So that's how you know it. And you can predict this by the atomic size. Okay, so that means in this case, if I go back here onto the periodic table, I'm going to look at between phosphorus and arsenic. Okay, so phosphorus is right here, arsenic is right here. Okay, so obviously between phosphorus and arsenic, phosphorus would have 3 energy levels, right? 3 shells, and arsenic would contain 4 shells. Therefore, it's clearly that phosphorus is smaller. Because phosphorus is smaller, the outer electron would experience stronger attractive force than the arsenic. Therefore, in this case, phosphorus would require more energy to remove an electron. Therefore, its first ionization energy would be the highest in comparison to the arsenic. Okay, now let's take a look at potassium and bromine. Okay, potassium is right here, bromine is right here. So these two contain 4 electron shells, right? 4 main shells. Okay, according to the number of N value that we see here. If you are not sure, you are welcome to draw the electron configuration as well, and you will see that the highest value of N is 4. Therefore, it will contain 4 shells total. Okay, these two contain the same number of shells. Therefore, you are not able to compare them by the number of shells. You need to compare them by effective nuclear charge. Okay, so we need to looking at their effective nuclear charge. Okay, the effective nuclear charge of potassium comes from the number of proton, which is 19. Okay, minus the shielding electron. Shielding electron are those in the inner shell electron, right? So that means in this case, if you want to know what are the inner electron, what you can do is you can write out the electron configuration, condensed electron configuration, right? So the noble gas that come before this is argon, right? Followed by 4s1. So we know that the outer shell is in 4s1, and that means everything else would consider to be the inner shell or the shielding electron. So that means the amount of shielding electron would be this inner is this core electron, which is the amount in argon, right? So if you're looking at it would be 18. So that means in this case, effective nuclear charge for potassium would be +1. Okay, you can do the same thing for bromine as well. Okay, so effective nuclear charge for bromine would come from the number of proton 35. Okay, and then what you are going to do is that you are going to write out the condensed electron configuration of bromine, which is going to start from argon, right, followed by 4s2, followed by 3d10, okay, followed by 4p, 1, 2, 3, 4, 5, 4p5. Okay, so you will notice that the outer shell would be those electrons that are in the highest n value. So it's gonna be this 7 electron right here. Everything else we consider to be inner core electron, which is going to be the shielding electron. Therefore, the amount of shielding electron would come from the number of the core, right, plus another n equal to 3 in 3D. Okay, so total would be 18 from here and plus 10, that would be 28. Okay, so therefore in this case we are going to minus 28, which is indicate the shielding electron or the inner core electron, right, is closer to the nucleus than those electrons that are in 4th level. Okay, if you subtract this, you are going to get effective nuclear charge equal to 7. Okay, clearly you will notice that electron in the outer shell, this electron right here, experience less attractive force from the nucleus, right, for potassium in comparison to the outer shell electron for bromine, right, experience stronger attractive force from the nucleus. Therefore, in this case, the electron in bromine would be harder to remove. Therefore, electron in bromine, the outer shell electron would require more energy to remove electron. Thus, their first ionization energy would be higher than potassium. Okay, so that's why it's bromine is the answer here. All right, I want you to use the periodic table here again and do ranking between calcium, oxygen, and chlorine. Okay, so let's pause the video now and then do this ranking. All right, let's take a look at your answer. So we are going to look at calcium, we're going to look at oxygen, and the other one is chlorine. Okay, so we're going to look at these three. Clearly, you will see that this is going to be the biggest, right, because contain the more number of shells. This would be the smallest. Okay, again, the smallest would have electron closer to the nucleus, harder to remove their outer shell electron. Therefore, it's going to require higher energy to remove electron. So that means the IE of the oxygen would be the highest. And because calcium is the bigger, right, so calcium is the biggest size out of these three, therefore the electron would be further away from the nucleus. It's easiest to remove, therefore it's going to require the least ionization energy out of these three. So the order would be calcium followed by chlorine, and then oxygen would have the highest ionization energy out of these three. Okay. All right, so this graph is the graph that plot between the group, right? So these are the main group elements, plot against the amount of the ionization energy, right? The unit is in kilojoule per mole. Okay, so every 1 mole of an element, right, is required this many kilojoule to remove the first electron. That's what it means. Okay, so you probably noticed that if we looking at the same group, right, group 1A, for example, hydrogen, lithium, sodium, potassium, as the atomic size increase, right, as you go down the column, as the atomic size increase, it's going to be harder to remove electron. Therefore, you are going to see that the amount of, it's going to be easier to remove electron. Therefore, in this case, you are going to see that the amount of ionization energy required to remove the first electron decreasing, right? So it would be the least for potassium. Okay, so and you also see another trend as well when you go across the period, as we mentioned earlier, right? As you go across the period, you will notice that the size will get smaller because effective nuclear charge becomes stronger, right? So the size becomes smaller. Therefore, it's going to be harder to remove electron. It's going to require more energy to remove electron. That's why you are observing increasing of energy, right, from left to right across the periodic table. Okay. Another one that I want you to note is that you probably notice that the noble gas require the highest amount of energy to remove their first electron. The reason for that is because the noble gases already have the most stable electron configuration. Therefore, to remove what is already stable, right, is going to require the most energy, because it's going to be the hardest to remove their electron, because their electron configuration is already in the stable form. Okay, and I also want to point out this deviation as well, that is, you probably observe that group 2A and group 5A is slightly increased, right? Is actually not follow the trend if you compare with their neighbors. The reason for that is because these two groups are part of the full field configuration and half field configuration that are relatively more stable than any of these. So that's why it's slightly going to be a little bit higher. Okay, so full field mean that the S, right, so the outer shell orbital S is already filled with 2. Half field mean the outer shell for P is already filled with 3 electrons. Okay. All right, so in summary, if you go, so this would be the trend for it, right? So this would be the trend for the atomic radii. And for the ionization energy, it will be the opposite, because as the size getting bigger, it's going to require less energy to remove electrons. So that's why the trend for the first ionization energy would be the opposite of the atomic size. And that same thing for the electronegativity value as well. Okay. So the next thing we're going to take a look at is we're going to take a look at successive electron, because in an atom, they contain several electrons. So therefore, we're going to take a look at successive removing electron. Okay, so the energy that involved with those, we call successive ionization energy. Okay, so it's reflect the energy needed to remove successive electron from the atom. Okay. So what do I mean by that? Okay, so I'm going to give you an example of sodium, for example, in this case. Right? So if you recall from the previous slide, I used the chemical symbol as X, but in this case, I'm just going to use a specific element. So I'm going to pick sodium. Okay, so in order to remove electron from sodium, sodium need to be in the gaseous state. Therefore, in this case, you will need to include the gaseous state. Okay, so as the electron is removed from the neutral atom, the product that become is going to be the cation, right, plus an electron as the product. Okay, the amount of energy that required for this process is about 500 kilojoule per mole. Okay, so every 1 mole of sodium is required this amount of energy to remove this electron. That's what it means, right? That's what the ionization energy mean. And you probably notice that this is have to be positive value as well, because this process is endothermic. It's indicate positive energy indicate that the system require the energy or consume or absorb that energy. Okay. So because sodium contain more than 1 electron, that means this you can also remove the second electron as well. Okay, so the second electron would be what is it would be the process using the product from the previous step. Okay, so the previous step we generate sodium plus, right? In order to remove 1 more electron, now sodium going to lose more. It's going to become sodium 2 plus another electron that is removed, and it's going to require another amount of energy. And you probably notice that this energy right here is actually a little bit higher than the first ionization energy. It makes sense because as you producing the ions, especially the cation, you are going to observe the atomic size decrease, right? We talked about the trend in the ions before. From neutral atom to cation, okay, the size get smaller. The reason for that is because when you are making cation, you are minimizing the electron repulsion, and you are going to increase the strength between the nucleus and the electron. So therefore, the size would shrink a little bit. Okay, so that's why once and atom become cation, the size will get smaller because of that. And as the size gets smaller, you will see that to remove the second electron is going to require more energy to remove electron. Okay. All right, so again, this is come from the previous lecture video that we talked about the size of cation. Okay. You can also do the third ionization energy as well, okay, by removing the third electron. Okay, so from Na2 plus, sodium still have more electron within the atom. You can remove one more. So removing the third electron, this is what we call the third ionization energy. Okay, so it's going to require higher energy also. Can you also add A after N? Okay, so this is sodium, so it's going to be Na. Okay, so don't forget to add this. Okay, so there's the typo right there. So again, same reason here. When you remove more electron, the size is going to get smaller and smaller. Therefore, as the size gets smaller, it indicates that the strength between the nucleus and the electron are stronger. Therefore, it's going to require much more energy to remove it. Okay. So what I'm going to point out next is we are going to take a look at the difference in energy between these three processes. Okay, so the difference in energy between the first ionization energy and the second ionization energy is equal to this amount. How do you get this amount? Well, pretty much you are subtract these two by each other, right? Same thing for this, right? The difference between these two is come out to be this amount. You probably see that the difference between the first and the second ionization energy is greater than the second and the third. This is what we call the energy jump. Okay, so we observe the energy jump between the first and the second ionization energy. Okay, so what does the energy jump tell us? Okay, the energy jump tell us that, well, if you draw the electron shell model of sodium, okay, so these are the electrons that involved with sodium. As you see, right, you can remove more than 3 electrons. You can continue removing all the way until you finish removing all of those. Okay, so in this case, I'm just choosing show you only 3 examples, right? So only 3 electrons, but you can literally just remove more than 3. Okay, so it's going to require more energy. That's all. Okay, so why is there a jump in energy? So that's what I'm going to take a look at next. Okay, think about this. This electron right here is further away from the nucleus, right? So in order to remove this electron, of course, it's going to require a certain amount of energy. How much? Well, it's going to be this much. Okay. Now, if you remove this one, what you are going to end up having is you are going to have the nucleus of the sodium, and you are going to end up with 2 electrons, right? So this is there are 2 electrons right here, and you are going to end up with, okay, oops, sorry, let me draw a relative size. Okay, so you are going to end up with 8 electrons total. Okay, so you're going to end up with 8 electrons. Now, remember the 8 electron outer shell is the same as the noble gas. Therefore, when you remove 1 electron, this is going to become a stable electron configuration, right? Because it's the same number of electron as the noble gas. Therefore, in this case, when you are removing the second electron, which is you are going to remove from what is already stable, therefore it's going to require much more energy for that. That's why you are going to observe the energy jump between the first electron and the second, because the second electron is in the inner shell that is already stable. And to remove the third one, it's going to be relatively higher, but it's still in the same shell. So that's why it's going to be higher by not much. Okay. All right. So this is a summary of this, right? So between 2 and 3, it's harder to remove the inner electron. Therefore, you are going to observe the jump between the first and the second energy. Okay. So if you plot the graph between the element, right, versus the energy required, again, this is the jump of energy that I was talking about earlier, right? So it's going from 500, right, about 500 to like 4,500. So that's a lot, right? So that's why we see that the reason why there is a jump in energy here, because this is the outer shell. This is referred to the inner shell. Now, what about magnesium? Okay, so I'm going to look at magnesium as well. Same thing for magnesium. Remove the first electron is going to require a certain amount of energy, right? Because you need to take it away from the nucleus that is pulling, so it's going to require energy. And as it become ions, magnesium ions would have a smaller size, therefore removing the second electron would require a little bit more energy. So that's why it's going from 700 to about 1400. But once you remove these two, you are touching the inner electron, which is the stable configuration similar to noble gas. Therefore, if you are going to remove the third one, right, you are going to observe the energy jump right here, right? So this energy jump for the magnesium tell us that this electron is the third electron, right, in the inner shell. Okay, and these two are going to associate with the outer shell valence electron because they not require a lot of energy like the third one in the inner shell. Now let's take a look at the next example of aluminum. Okay, so aluminum, if you're looking at aluminum contains 13 electrons. Okay, so that means if you draw the electron shell model, you will notice that there are 3 electrons in the outer shells. So same analysis here. Okay, removing the first electron is going to require a certain amount of energy. And once this removed, you will notice that the size will get a little bit smaller because you are minimizing the electron-electron repulsion and you are increasing the nucleus and electron attraction. Okay, and to remove the third one, to remove the second electron is going to require a certain amount of energy as well, which is going to be higher than the first ionization energy because in this case, the second electron now is going to experience stronger attractive force from the nucleus. Therefore, the second ionization energy would be greater than the first one. Okay, now it's going to, you'll notice that this is neutral. Once it loses one, right, it will become aluminum plus. Once it loses one more, then it's going to become aluminum 2 plus. Okay. Now, if we remove the third one, okay, so if we remove the third one, of course, this third one is going to require higher energy than the first and the second ionization energy because the size of this now is getting smaller. This electron experience stronger attractive force from the nucleus. It's harder to remove this electron, therefore it's going to require higher energy to remove it. Once we remove this, then aluminum 2 plus will become aluminum 3 plus. So you probably notice that I remove one at a time, right? So when we are removing electron, we have to remove one at a time, okay? So now when you look at aluminum 3 plus, you probably notice that the electron configuration now is the same as the noble gas neon, right? So it's have 8 electrons as the outer shell. So this configuration is already stable. So that means if you are going to remove the fourth one out of this stable configuration, you are going to require much higher energy to remove it because the nucleus doesn't want to let go of that electron. In order to pull it away, it's going to require much more energy for that. So this is when you are going to observe the jump, right? So this is where the energy jump comes from, because if you remove this one right here, it's going to become less stable, which is aluminum 4 plus. Therefore, in this case, what is indicate is that this energy jump here is indicate that the fourth electron that you are withdrawing, which require much higher energy, would indicate is the first electron in the core shells, right? And everything else would consider to be the number of valence. Therefore, in this case, because there are 3 value of ionization energy, is going to associate with the 3 valence electron, right? And the fourth one would be the core electron, right? The fourth one would be the core electron because it requires much more energy to remove from the stable electron configuration. Okay, so this is really important because you are going to see the application of this in the next example. The successive ionization energy can tell you about the number of valence electron for each element. Is also going to allow you to predict the location of that element in the group as well. For example, in this case, because we know aluminum contains 3 valence electrons, therefore in this case, aluminum would be in group 3, in the main group element 3, right, or 3A, okay, or 13. Okay, so now let's take a look at example 8. Okay, so what do I mean by that? Okay, so one thing I want you to actually write this out is we are going to consider these only the main group element. Okay, because the main group element is the one that follow the trend the most, right? So we are going to consider the main group element. Okay, so let's take a look at how can we determine the identity of the element just from the successive ionization energy. Okay, so in order to do this, you need to do exactly what we did earlier, right? You need to find out the jump of the energy, because the jump of energy will tell you about the core electrons and the number of valence electrons. So we're going to do the same thing here. So pretty much find the difference between each of these, right? So the difference come out 776 kilojoule per mole between the first and the second ionization energy. Continue doing this for the rest of these. You are going to observe that the biggest difference in energy appear between the fourth and the fifth ionization energy. Therefore, in this case, I can say that the fifth electron that associated with the fifth ionization energy, this electron here is part of the inner shell electron. Therefore, how many outer shell electron then? Well, it's going to be 1, 2, 3, 4, right? Because there are four electrons before it's jump, right? You remove those 4 before you observe the energy jump. So in this case, the outer shell electron would be 4. Okay, so for electron, if you are looking at, right? So for outer shell electron, so for valence electron is going to associate with group 4A. Which is the main group element. Okay, so that would be this choice right here, right? So any of these in this group. Okay, what else that the problem give us? Okay, so the problem give us that is located in period 4, right? So it's tell us that it's located in period 4. Therefore, in this case, we are going to look at group 4, period 4. Okay, so we already see this is group 4. Period 4 would be, okay, so where is the period 1 start? Okay, period 1, remember this is period 1 right here. It starts from helium and hydrogen. Therefore, you need to count this as 1. The carbon would located in second period, right? This is 3, this is 4. Therefore, the answer would be germanium, right? So C would be the answer for this. Okay, so that's how you use the successive ionization energy to tell about the location of element on the periodic table. Okay, all right. So here's another data that you can look at that help explain what I just explained earlier. Is the same thing, but just look at this in different data format. Okay, so what we have here is that it's different element. Okay, here are their electron configurations. Here are their successive ionization energy, right? IE1 associated with the removing the first electron. This one associated with the removing the second, right? This one associated with removing the fifth electron. Okay, so if you're looking at the valence electron for lithium, beryllium, all the way to like neon, you will see that these are the outer shell electron, right? Because the highest n value are 2, this is going to indicate the inner shell electron. You probably notice that the first ionization energy of removing the first electron from all of these, right, is going to increase, right, going from lithium to neon, because as the size getting smaller, it's going to be harder to remove, right? So that's why you are going to see the ionization energy is increasing with that trend. Okay, so what I want to point out with the successive ionization energy is that if you're looking at lithium, okay, so lithium contains only 1 valence, therefore the first ionization energy would be a certain amount. But when you remove the second one, this is when you are touching the core electron now. So you are going to see that there is a jump in energy from 500 to 7,000, right? Because you are removing electron from the stable electron configuration. Okay. Same thing if you're looking at beryllium as well. Beryllium has 2 valence electron. So the first 2 ionization energy, right, is going to be relatively similar. But when you are remove the third one, you are going to touch the core electron. Therefore, the energy would jump, right? You probably observe here, right? So 1700 jump to like 14,000, right? So that is a big energy gap right there between IE2 and IE3. Indicate that there are only two valence, and the third one is going to be come from the stable configuration. Okay, same thing for boron as well, right? So we have three valence electron, and you are going to see three valence electron have a relative similar ionization energy, right, by increasing as you remove for each of those electron. But when you are removing the fourth one, it have to come out from the stable configuration, which is the core electron. Therefore, the energy would jump by much, right? So this is only like what, 3600. This is jump to 25,000, right? So that's the energy jump right there. Next, we are going to take a look at the trend of the electron affinity. Okay, so what is the electron affinity? The electron affinity is the amount of energy involved adding an electron to a neutral gaseous atom. Okay, so it's kind of like the opposite of the ionization energy that we looked at earlier. Ionization energy is the energy required to remove electron. This one is the energy associated with adding an electron. Okay, so let's take a look at an example of chlorine. Okay, so if you have chlorine atom in gaseous state, okay, to add electron would be part of the it would be part of this, right, this side, because it indicates that the neutral chlorine is accepting an electron, and as neutral chlorine accept electron is going to become chlorine minus or chlorine anion. Okay, so in this case, in order to add electron to it, okay, this process right here for chlorine or for group 7A, this process is actually going to produce energy. Energy would be part of the product. So because energy is on this side, it's going to indicate that this process is releasing energy. Okay, so this process, because release energy, you are going to observe the negative value of the energy that associated with it. Because the energy is negative, it indicates that this process is going to release the energy. Okay, so the negative electron affinity tell us that the system release energy, and is also indicate the strong attraction between the atom and the electron as well. So this process is called exothermic. Now, if you compare this with the noble gas group, for example, argon. Okay, so as argon accept electron is going to be argon minus. Okay, electron would be part of the reactant or part of the what we input, right? This is the output, this is the input. The arrow tell us that this is what it's become, right? So as argon neutral accept electron, it's going to become argon minus. Remember, the noble gas already have the most electron configuration. It doesn't want to lose or gain any more electrons. So in this case, this process is not favorable because argon doesn't want to accept any more. But it can happen. If you want this to happen, then you will need to actually add energy to it. Therefore, the first electron affinity or the first adding electron, right, the energy involved with this going to be a positive value, right? So that's greater than 0 is indicated as positive value because the interaction between argon and electron is weak because argon doesn't want to accept any more electrons. So this process would be endothermic. So the takeaway message for this is that you are going to see that the stronger attraction between an atom and electron, you are going to observe a more negative value of the electron affinity is indicated it's going to be more exothermic. Okay, so that means when we talk about exothermic or the system releasing energy, the more exothermic is going to indicate a stronger attraction between atom and electron. Okay, so or the value of EA would be the more negative. The trend of the electron affinity can be predicted using atomic size also. Okay, so there are two things we're going to take a look at. The first trend would be go down the column or go down the group on the periodic table. As we go down the column, we see that the atomic radii increased. Therefore, the atomic size increased, right? So that means that if you want to add electron, it's going to be harder to add electron because the strength of the attractive force between nucleus and electron are weak because it's really big. It doesn't want to hold more of the electron. Therefore, in this case, it's harder to add electron. Is going to refer to a weak attraction between adding electron and nucleus. Therefore, you are going to end up with a lower magnitude of, or what do you call it? It's going to be a less exothermic for the electron affinity. Okay. Versus if you go from left to right across the periodic table, you are going to observe that the atomic radii decrease because you are increasing the effective nuclear charge. The size would decrease, right? Therefore, as the size decrease, it's going to be easier to add electron. And because it's easy to add electron, it's going to indicate that the interaction between the nucleus and the electron are strong, right? So that means in this case, the electron affinity would be more exothermic or more negative, right? The magnitude will increase in this case. Okay, so note that the only thing that is exception is the noble gas, right? The noble gases are always going to be a positive EA, or what do you call it, an endothermic for that. Okay. All right, so let's take a look at an example here. We are going to look at more negative electron affinity, which means, oops, sorry, let me actually do this first. More negative electron affinity is going to indicate that stronger attraction, right, between nucleus and adding electron. Okay, so we already see that as the atom is big, right, versus a small atoms, right, this one, if you want to add more electron to it, the interaction between the nucleus and the electron is going to be weaker, right, than the one that is than the smaller size of an atom, right? So the interaction between these would be stronger. Okay, therefore, the weaker interaction, you are going to end up with less exothermic, right? Which means that the electron affinity would be less negative. Whereas if you have a smaller size, indicates stronger attraction force between nucleus and adding electron, this one is going to be more exothermic, right? So the EA value would be more negative. Okay, so that means if you're looking at between oxygen and neon, you will see that, wait a second, oxygen is not the noble gases, right? But neon is. We already talked about this earlier. Neon doesn't want to add any more electron or accept any more electron because the electron configuration is already stable. Therefore, in this case, in order to add electron to neon, is actually going to require energy to add to it. It's not going to release energy. Therefore, in this case, the one that is more negative or indicates stronger attractive between nucleus and the adding electron would be oxygen. Between potassium and bromine, okay, so because bromine is going to be smaller than potassium because effective nuclear charge of bromine is higher, right, with the same energy shells. Therefore, in this case, bromine would have ability to attract electron with the stronger force. Therefore, it's going to be more exothermic. Okay, so here is the value of the electron affinities. Okay, so pretty much it's really difficult to make the generalization of electron affinity. But what I want you to know is that just know the general trend, okay? Because on the exam, you will not be given this table, but what you need to know is the general trends. Here is the exception that I just mentioned earlier for the noble gas. Okay, so the next thing we are going to take a look at is between group 2A and 5A again, right? So you probably see that this is break the trend. So this is when it's break the trend. The reason for that is because these two are the half field and full field configuration that are relatively more stable. So the last trend on the periodic table that we are going to take a look at is the metallic character. Okay, metallic character is the trend for metals. Okay, so metals tend to lose electron in chemical reaction. Okay, so that's the trend of it. When we talk about metallic character, you are going to look at the ability for the atom to lose an electron. Okay, so metal are most likely to lose electron, and here's why. Okay, so if you have sodium, you probably notice that it's contain the outer shell electron just one, right? So to lose these to become like noble gas is easier. So that means in this case, sodium is most likely to lose electron because it achieves stable electron configuration right away as it loses electron. However, if you're looking at chlorine that is non-metal, you will see that chlorine has several more electrons. So if in order to lose this, it's gonna have to lose 7. But if it's accept, it's have to accept only just 1, right, to be like the noble gas. So in this case, if it's lose 1 more here, this chlorine ion still not achieve the stable electron configuration. Therefore, in this case, chlorine will not going to lose electron. Is most likely to accept electrons. So that means in this case, chlorine would doesn't have the metallic character, right, compared to sodium. So pretty much, if you're looking at the trend for the metallic character, it's going to be the same trend as the size again. Okay, so it's similar to the size again. Think about this, as the size increase, right, when we go down the column, as the size increase, we already see that it's going to be easier to remove electron. Therefore, in this case, the metallic character would be, would increase, right? So it's because easier to remove electron. And you can tell this by the trend of the ionization energy as well, right? So it's going to exhibit more metallic character. On the other hand, if you move across the period from left to right, as the size decrease, it's going to be harder to remove electron, require more energy to remove it. Therefore, it's going to exhibit less metallic character. Okay, so pretty much when we talk about metallic character is the ability of losing an electron, right? So that's what we are talking about here. So calcium and arsenic have the same number of shells. If you're looking at these two contain 4 shells. Okay, but calcium is on the left side, arsenic is on the right side. So this one going to have less effective nuclear charge, right, than of the arsenic. Okay, so if you compare the effective nuclear charge, as the effective nuclear charge increase, you are going to observe that the size of the arsenic would be smaller than the size of the calcium. And for the atom to lose an electron, is going to lose electron easier for calcium because the electron is further away as the size bigger in comparison to arsenic, right? So in this case, you are going to observe that calcium would exhibit more metallic character because of that, because it's bigger, most likely to lose electron than arsenic. Okay. Same thing if you compare between silicon and tin. Okay, so these two are in the same group. So these two are in the same group. Okay, and that group is group 4A. Okay. Silicon contain only 3 layers. Okay, so silicon contain only 3 layers. Okay, so if this were nucleus, so it's contain 1, 2, 3, versus tin contain 5 layers, right? 5 energies level. So 1, 2, 3, 4, 5. So obviously tin has a bigger size than silicon. So in this case, the outer electron right here going to experience less attraction force from the nucleus. Therefore, it's going to be lost easily, right? In comparison to this electron that is closer to the nucleus. Therefore, in this case, tin would exhibit more metallic character than silicon. Okay, so because easier to lose electron. Okay, so again, so pretty much everything that we talk about is going to base on the atomic radii trend that we discussed in the previous video. What you need to understand is that the explanation for the trend of the atomic radii, there are two things. One is the size, right, or the number of number of shells. Okay, if one has more shells than the other, clearly the size would be bigger, right? If you have the same number of or same number of shells, then the next thing you're going to take a look at is effective nuclear charge, right? The higher effective nuclear charge, the size would be smaller. Okay, so that's going to explain the atomic radii that we discussed in the previous video. Okay, and this size is going to have to, it's going to help determine the metallic character as well, because as the size gets bigger, the atom going to lose electron easier because the outer electron is further away from the nucleus. Therefore, that the bigger size of atom would exhibit more metallic character. Okay, so therefore, if you looking at this, right, so that's why when we talk about metal versus non-metal, you will notice that all of these, right, pretty much of these here, these are pretty much metal. Right. The reason for that is because all of these are most likely to lose electron in comparison to this side of the periodic table, right? So this is the non-metal. So they are most likely not to lose electron. Okay, so that's why we have two different two category on the periodic table. Okay, based on the ability of them losing electron. Okay. Now, the energy that involved with removing electron, the first electron especially, is the first ionization energy. The En is the ability of an atom to attract electron to itself. You will see that this would be the opposite trend in comparison to atomic radii, because as the size increased, right, as it's getting bigger, as the size increase, we are going to, the electron is, will be lost easily. It doesn't require much energy to do that. Therefore, the trend for the IE would be the opposite. Okay, and as the size is big, they are not going to attract electron very well. Therefore, you are going to see the decreasing of the electronegativity value as well. Okay, so that is the same trend for the electron affinity as well, right? So the stronger interaction between nucleus and electron is going to be more negative or more exothermic. Okay, so except noble gas. So therefore, in this case, as the size decrease, is going to be able to accept or attract more, attract electron better. Therefore, it's going to be more exothermic or more negative. Okay, so that would be, so these three are going to be the same trend, and these two are going to be the same trend. Okay. All right, so here are pretty much everything that we talk about in the trends of the periodic table. So please start working on the homework